Okay, this is the worksheet 3. I just gotta show you this because I think it's cool. But I've been reading this book with my daughter because it's never too early to do organic chemistry. And I will say, this is the thing that is terrible. So if any of you ever write educational books, don't change the colors of the atoms. Oxygen's supposed to be red, hydrogen's supposed to be white. When you get the molecular model kit, you'll see this. Carbon's supposed to be black. Nitrogen's supposed to be yellow. Hold up, Abigail. So, don't get the colors wrong. Otherwise, everything else in this book is not too bad. Right? You can see your line structures, and my daughter can tell you what benzene is. So, you know, that's pretty good. All right, that's it on this. Okay, now let's actually do this worksheet. Okay, so nomenclature. Again, here's kind of like the steps that I go through for nomenclature. Find the longest chain, and you want to have the longest chain with the most number of substituents. Right, so if you count them, there's multiple chains that have the largest number of substituents. Suppose that 2 of them have 8. So right. Suppose that this is 1, 2, 3, 4, 5, 6, 7. It's shorter, so this is the longest one. You kind of number it both ways, and then you do it this way. But if you had 2 that were the same, and 8, you do the one that had more substituents. Okay, now there's 2 different ways we can number it. It's left to right and right to left. So the way you want to do it is you want to look at what numbers are the substituents are on. So for the red ones, it's going to be on 1, 3, 4, and 6. So, all right, I'm getting ahead of myself. I always do this because, whatever, I'll finish this. The blue one is going to be 3, 5, 6, and 8. Sorry, this is step 3, find the lowest numbering system with the most substituents. But I should actually name all these things. So we're going to have this for, I'll circle the substituents. This is cyclobutyl. You know cyclobutyl because there's 4 atoms in the ring. This is methyl. This is propyl. And this is fluoro. I think I need another book to prop this up. Okay, this doesn't get all. Prop this up. Yeah. Okay. So now I've done steps 1, 2, and 3. The red ones are the lower numbering system, and you would go by the first substituent you get to, and then the second one, and then the third one. So it's not like you add them all up. It's just you go by the first one you run into, which one has the lower number. If there's a tie there, you go to the next one, etc. Okay. So now when I name this, it's gonna go alphabetically. So it'll be 1 there should be C. Cyclobutyl. I guess this is 6 fluoro. And then M comes before P, so it'll be 3 methyl. 4 propyl. Octane. Parent chain is an octane because there's 8. It's a alkane, functional group wise, so it's going to be ane. All right, let's do the second one now. So for this one, we're going to have 2 ways that make sense because we want the lowest possible numbering system. You could just look at this and see the ring is longer. You can't do something like this where you number part of the ring. The atoms that are part of the ring are only part of the ring. They don't count for anything else. So this is like a 3 carbon chain or a 1 carbon chain. You can't do 7 going through the ring. So there's this numbering system, and then there's this one. These are the only ones that make sense. Actually, if you look at the numbers, they're going to be 1, 2, 3, and 5. Let's do substituents. I should actually do this the way I taught it. This is going to be methyl, fluoro, bromo. Right? Should let you actually see this as octane all the way to the end. You can't see all of it. Okay, good. All right, so now that I did that, I want to see which one's going to be the correct numbering system. Since the numbers are going to be for blue, which ones are blue? 1, 2, 3, 5, and for red, it's also going to be 1, 2, 3, 5. They're the same number, so now you go alphabetically. So the red one's going to be the correct one because B comes before M. Let that just be in the video for a second. All right. So now that that is there, now my parent chain is going to be a cyclohexane. Right? My substituents are going to go alphabetically, which the red numbers are the correct one. So it's going to be 1 bromo. Hopefully I did this right so it all fits. 2 chloro. 3 methyl. 5 propyl. Cyclohexane. No space. That's supposed to be all one word. So when you get to the end of the substituents, there's no dash or anything to get to the end of the cyclohexane. It all goes together like that. All right. These other ones I will do a little bit faster because I think you kind of see the point of what I'm doing, and I don't want to take forever with this video doing these. So these are my substituents. This is going to be 1, 3, and 5, no matter how you number it as the lowest scheme. So when I do this, E comes before M, so the correct numbering is going to be this way. These are methyls. This is ethyl. This is going to be 1 ethyl. Then it's going to be 3, 5 dimethyl. And the di does not count for alphabetizing this. It's the M that counts. Cyclohexane. All right, now let's count the longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. Bet you that's the longest one. Yeah. It might take some trial and error to find out which one's the longest chain here. So now let's look at our substituents. We got methyl, as well as that one. We got isopropyl. We got ethyl. This I counts for alphabetizing. If you got something like a tert-butyl group or something like that, the tert or the T does not count. For iso, it does. I don't make up the rules. All right, so this is going to be 6. Is this the right way? Yes, this is the right way because it's going to be 2, 3, 5, 6, as well as 4, 5, 7, 8. So this is the right way. So 6, ethyl, 2, 3 dimethyl, 5 isopropyl, and then you just do no name. All right, let's do this last one. 1, 2, 3, 4, 5, and 4. So I'm gonna want to number this way so I get the lowest number. So my cyclobutyl, my bromo, and my methyl. Bromo, methyl. And now this is a pentane, so I'm gonna just do this alphabetically. 2 bromo, 1 cyclobutyl, 3 methyl, pentane. So that you can see the whole thing. All right, that's the name of that. Now we're gonna draw the molecule from the name. You want to sit on my daddy's lap? Okay. Sit on Daddy's lap. All right, so the way you do name the structure is you're going to draw the parent chain, which is at the end, cyclohexane. And then I'm just going to number it. On 1 and 2, I have methyl groups, and on 4, I have an isopropyl. Heptane, that's 7. On 2, I'm going to have a chlorine. On 4, I'm going to have a methyl. 5, I'm going to have a methyl, and 5, I'll also have a bromo. This is pentane. Oh, sorry, cyclopentane. What does it say? So on 1, I'm going to have a butyl. 1, 2, 3, 4. On 2, I'm going to have a chloro. On 3, I'm going to have a methyl. Heptane. Sorry, there should be an E on the end there. This is a heptane, 1. So on 2, I'm going to have a methyl. 4, I'm going to have a bromo and an isopropyl. 5, I'm going to have a methyl and a chlorine. Like that. Okay. These are functional groups. So this is going to be carboxylic acid. This is going to be an ester. This is going to be a benzene ring, or an aromatic ring, it might be called. This is going to be called a phenol. It is different than an alcohol. It does have a benzene ring in it. The benzene ring is like part of it, but it's different than an alcohol. This is an amine. This is an alcohol. This is an alkene. This is an ether. And that's what we got there. pKa's of the underlying ones. This is going to be about 5. This is of an ester, so it's going to be about 25. And then this is about 40. I encourage you, even though Dr. Falvey is going to give you these things by on a table for your exam, I encourage you to memorize the pKa's. It will just save you time. These are about 10. This is about 16. This is about 40, 45, something like that. I think these might be 45. I want to say they're 45. This is going to be about 10. This is going to be about 50 to 60. This will also be about 45 for the pK. So there they are. All right, draw the correct curved arrows. The oxygens, remember you have dipoles this way. And so what happens is this lone pair is going to come grab that hydrogen this way. And we are going to protonate. This is called an epoxide. That's the functional group. Plus Cl minus. All right, these are resonance, so you should be able to do these. See the structure. All right, this is going to be acid base, so I'm just going to draw out one of those hydrogens, still positively charged, just expanding one of them, so that these lone pairs can come and grab that hydrogen.
Do you want to be hot? No? Okay. Yes?
Plus the lone pair. Good. Now for this one here, these might be harder to see. If you don't see this next one, that's okay. This is something we're going to do later. But there's actually partial positive charges on here. And this is going to go this way. You want me to take this? You want to sit on Daddy's lap again? Alright, come on. Sit on Daddy's lap. Alright, come on. Dad, I gotta still write and talk. So we're gonna break this bond here, so the bromine's still gonna be attached here, but no longer this carbon. And we're gonna have the oxygen attached here. And have 2 carbons come off.
2.
And then this nitrogen's lone pair is gonna come and attack the positive charge. We're gonna make a sigma bond. Like that. There is still 1 lone pair on the nitrogen. Alright, let's turn the page. Alright, these are resonance structures for a phenoxide, which is a deprotonated phenol. And this is actually why phenol has a very different pKa than an alcohol. It's because you have these resonance structures.
Red.
You have to draw in the arrows in red so they're easy to see. Oh, don't hit that. You need to be able to see the video.
Two.
Can you get down? Ease down. Like that. All right. These are also resonance structures. Having good practice and being able to do your resonance structures well is very important. Resonance tends to be one of the things students struggle with the most on their first exam, and not usually in organic too, but and for a lot of organic 1. Resonance structures are always showing up. All right, and then we have positive resonance. Remember, there's 2 arrows in negative resonance. There's 1 in positive resonance. The arrows go towards the charge in positive resonance versus they go away from the charge in negative resonance. All right, and then this chloride is gonna come and attack there. Push that up. This is just like the bromine one we had earlier. This is the chlorine that's right here. This chlorine is this chlorine. I have water coming and attack there. I know I'm doing this fast. I just don't want this to be an absurdly long video. A lot of these things, these weird ones that you see like this, we will do again this semester later. All right, acid-base reactions. So this requires no pKa. The pKa of an amine is like 35. The pKa of a carboxylic acid is like 5. So draw the conjugate acid. This will be my acid. This will be my base. I have to draw mechanistic arrows. It's going to take this proton, and they're going to come back on that oxygen there. So conjugate base will look like this. Conjugate acid will look like this. The pKa of the conjugate acid is about 10 versus this pKa is 5. Calculate the KEQ. So I don't remember if I'll be talking about this, but you don't need to know this. I just want, if he doesn't talk about it, you don't need to know it. I just want to do this so that you understand the significance of a pKa. But the KEQ is equal to 10, the pKa on the right, or the conjugate acid pKa, minus the pKa on the left, or the acid pKa. This is going to be equal to 10 to the 10 minus 5, which is equal to 10 to the 5. Now, what this number means is that for every 1 reactant, you have 10 to the 5th products. So for every carboxylic acid you have with a proton on it, you have, what's 10 to the 5th? 100,000 deprotonated carboxylic acids or carboxylates, right? If this exponent is positive, is above 0, then the equilibrium is going to lie to the right. Equilibrium always pushes away from the stronger acid. Remember, something being an acid means it gives up a proton. So if this is a stronger acid, the equilibrium is going to be on the other side. think we're almost done here. But so this pKa is 16. The arrows are going to be this way. Since you have a negative charge, if it has a negative charge, you know it's going to be the base in an acid-base reaction. And then we got to look at an alkyne. You'll see its pKa is 25. And then we have our conjugate base, conjugate acid. This is our base, this is our acid, right? So what's the KEQ? It's going to be 10, or KEQ is equal to 10. The one on the right, 25, minus the one on the left, 16. It's going to be equal to 10 to the 9. So 10 to the 9 means that for every one of these, you have 10 to the 9th of these. Equilibrium lies to the right. All right. This one, the pK is minus 7 versus 16. HCl is always going to be the acid if it's there.
Oh, pot cake. Good memory.
All right, and then this is going to be our conjugate base. This is our conjugate acid. This is our acid. This is our base. And this pK is about 0. That one's minus 7. So the KEQ now is going to be 10 to the one on the right, which is 0, minus 7, which is equal to 10 to the 7th. So we 1 to 10 to the 7th, which is going to be favor the equilibrium going to the right. That's the last problem. All right, that's it for this worksheet. Good luck studying. Sorry that not everyone got discussion today because of the snow. So that's it.